Good morning to one and all. I'm pleased to introduce Dr. Carlos Lopez-Martinez, a distinguished figure in the fields of electrical engineering and remote sensing. Dr. Carlos is an accomplished individual who has dedicated his career to the field of electrical engineering and remote sensing. He holds a master's degree and a PhD from Technical University of Catalunya, Barcelona, Spain. In addition, he furthered his expertise with a postgraduate diploma in data science and big data from University of Barcelona. Currently serving as an associate professor at Technical University of Catalonia, Dr. Carlos' professional journey has spanned international borders. With significant experience at renowned institutions such as BLR in Germany, the University of Rennes in France, and as a group leader of the remote sensing and natural resource modeling team at the Luxembourg Institute of Science and Technology, he brings a wealth of global insights to his work. His research interests are diverse and cutting edge, encompassing areas such as synthetic aperture radar theory, SAR Polarimetry, multidimensional SAR, and advanced digital signal processing. Dr. Carlos has authored over 200 articles in prestigious journals, books, and conference proceedings, showcasing his commitment to advancing knowledge in his field. Notably, he has received several accolades, including the USA 2002 Conference Student Prize Paper Award and IEEE-GRSS 2013 Gold Early Career Award. Despite his impressive achievements, Dr. Carlos remained deeply involved in academia, offering his expertise in teaching at various levels from bachelor to PhD programs. Beyond his academic endeavors, Dr. Carlos has actively contributed to space missions such as Spanish PASS, Europe Space Agency SAR, demonstrating his commitment to real-world applications of his research. He also holds key roles in professional societies, serving as an associate editor for the IEEE-GRSS Journal and MDPA Remote Sensing. Dr. Carlos brings a wealth of international expertise and genuine passion for the practical implications of his research. His commitment to education and collaboration is evident in his humble yet impactful contributions. Now let's warmly welcome Dr. Carlos.
Thank you very much for this introduction. I'm very pleased to be here, and also I thank the organization for inviting me to this tutorial that, as said before, is going to focus on SAR polarimetry for current and new missions. So just before starting some logistics, we have agreed at least stop with this for 3 hours, to stop each hour kind of 5 minutes, just to have time to decompress it, okay, because 3 hours is a bit too much. Also, I would like to inform that this tutorial is connected with the SAR collocated workshop afterwards, because here I will talk about the theory of SAR polarimetry, how to extract information about potential applications, and later on, people from SAR will focus on missions, how polarimetry can be the mission, and at the end, we will work in a demo tutorial about all the theory that we have presented. So before we start, here you have my contact information. So I'm really glad if you send me questions or you contact me. So it's completely up to you. I'm really open. I don't answer emails from 1 minute to the other because my relationship is very good, I have to admit. But I try to answer all the evenings. You can contact me also through email. So just before to go, together with Armando, this afternoon we will run a demo session in the last hour of the SAR collocated workshop. So the data we will use, the polarimetric data, the code, so are accessible through this direction. So you can scan the QR code, or you can go to this web address. So there you will have access to the Google Drive, where you can download the data, where you can get the code. So I will let this information for you. Okay. In the afternoon, the demo session, the lab session will be a demo because it's only 1 hour. So together with Armando, maybe Armando will run all the things, we will show all the things, but in order for you to have access and to play at home with the data, you will have access to all that. Okay? So you have access to the Python code, the data, in the cell phone data. Everything is accessible to this app. Okay, so if you want, You can scan with your mobile phone, or you can make a picture and then you can add it to it. So we have checked this morning and everything. If someone is not able to access, so please let us know. Okay? Everybody has the information. Later on, we will put again. Okay, so let's go. Starting this tutorial with SAR Polarimetry. So in order to set the basis of this polarity, as in the talk we presented yesterday, I will go first with synthetic aperture radar because we are doing polarimetry with radar. So we need to know the basis of the radar because at the end, the basics of this synthetic aperture radar will determine how we will access, how we will extract the geophysical information, geo and geophysical information we will extract with polarity. So I cannot start from the scratch polarimetry. I could, because polarimetry is something used in other domains, in optical domains, and also many other scientific domains. But the way we use polarimetry needs the introduction of the basics of synthetic aperture radar. Then we will go about wave polarimetry. What do we mean with polarimetry? I will try to answer this question here. And then scattering polarimetry is how to use polarimetry to infer properties of the targets we are looking at. So let's go with synthetic aperture radar. If someone of you have questions, just raise your hand and I will try to answer the question live. Okay? Or afterwards, or during the whole conference, I will hear while I will give that to answer the question. Okay, so what is a radar? A synthetic aperture. So a synthetic aperture radar, in the way we look at it, it's mainly a satellite equipped with a classical radar. So the idea is that this radar is moving to a trajectory. Okay, so we are recording the echoes at each point of this satellite on the trajectory. We will have two dimensions, range and azimuth, and we will produce images, matrices of points into this domain. What are the main properties of the synthetic aperture radar? First of all, it's a side-looking geometry. We are not looking down, we are looking at one side, so therefore this will introduce some distortions on the images. We obtain two-dimensional data, we obtain matrices, pixels arranged in a matrix, the dimensions are range and azimuth. We have different image modes. I won't enter into the analysis of these image modes, but basically this mode on the compromise between spot coverage and spatial. So basically, we would like to have the largest image possible at the finest resolution. So we have different imaging modes that basically tackles compromise. And finally, the most important characteristic of SAR images and is the images are complete. They have an amplitude and a phase, because in order to form, as I will let you know now, to form this combination of echoes at reception to have or to increase the azimuth resolution, we need this, or we need to record the E and Q channels, the real part, the image part of the signal. Also, in the second part of the tutorial, I will analyze the implications of that nature in terms of the statistical signal. So, how does a synthetic aperture radar works? So we have to divide the function of the radar in how it works in range, how it works in azimuth. So in range, which means basically the direction between the radar and the target, okay, what we have here is the system transmitting some kind of series of pulses, okay? So basically, we send pulses to the ground and we receive back the echo. How do we determine the resolution dimension? What I mean by resolution, the capability to differentiate two targets into this dimension. So basically, it's like any classical radar in the way that the largest, the bandwidth, okay, we can go, for instance, from systems having 6 megahertz bandwidth, like the future biomass,
to system having 300 megahertz. So we can tens of meters to something below the meter. How does it work in the other direction? How do we obtain azimuth resolution? So in a classical antenna theory, basically the resolution in the azimuth is determined by the dimension of the antenna. So as you may imagine already, in a satellite, we cannot have large antenna. So therefore, we have radiation of the antenna. The radiation diameter is, so the resolution in azimuth is very poor. How do we increase the resolution? Of course, by having larger antennas. So we cannot put a kilometer-wide antenna into a satellite. So the way is to make a larger antenna in a different way. So we have already this solution on ground, either a very array feasible in a satellite, in a space, because we something in space. So the basic idea, because the synthetic aperture radar, is not to have many copies of the same antenna, but to have a single antenna traveling across. Therefore, what we make is to record the echoes at each as traveling size a large antenna. Doing that, and here you have the equations that basically confirm what I have explained to you. So in a normal radar, basically the azimuth resolution depends on the angular spread of the antenna and depends on the distance from the radar. And this is a very poor quality. Nevertheless, if we go to the equations for the synthetic aperture radar, we can see that finally the azimuth resolution is in the order of the dimensions of the antenna. So normally we have antennas in the order of meters, so therefore we obtain azimuth resolutions in the order of meters. And therefore, this resolution is very useful for Earth observation applications, because at the end, combining range and azimuth, we can have resolutions in the range of meters. One moment. Okay, so what happens at the end? If we combine the resolution in range and the resolution in azimuth, at the end, combining all the ideas, all these ideas, we can derive the impulse response of a radar system. Is how the radar system looks at the ground. So basically, the impulse response of our system is nothing more than one equation like this. So basically, our impulse response is this double sync. Of course, in the ideal case, we would like a delta function, but this is not possible. It would mean infinite bandwidth, infinite large antenna. So therefore, we face the limitations. And the width of this impulse response, so basically, is the azimuth resolution and the space resolution. So therefore, we want this impulse response the narrower possible to increase the detail. So basically, at the end, the SAR image is nothing more of the convolution of the scene with this filter. So what we obtain, a SAR image, is a convolution of the real scene with this impulse response. So this impulse response, and we will see it, along all this tutorial, the importance of this idea, because this impulse response determines how we deal with the geophysical and biophysical information. The main idea to keep this is that this area, or the area covered by this impulse response, is what we call the resolution cell. And the resolution cell, at the end, the pixel, basically is a pixel of one dimension in azimuth and one dimension in range. Okay? So therefore, we create one pixel. Okay? Here we have one collection of systems, how we can have a satellite describing a trajectory. First of to board the satellite, sorry, the radar into a satellite. So this is what we have. The first SAR system on the space was the CSAT in the 70s, and since then, here you have a full collection. It's not complete, okay, we have many, many more, but as you can see, all of these systems work at different frequencies, with different revisit times, with different coverage, with different polarization, and so on. The advantage of these systems is that they can provide global coverage. Okay, and this is a very good advantage if we want to address global issues, like, for instance, the climate change. Another way to do that is to pour the radar into a plane. Okay, we have a flying system. Okay, here you have a collection of airborne systems from all type of space agencies. Okay, in Canada, in Germany, in France, in Denmark, in Japan, all of them working for different types of applications. The main idea of these systems is that they can provide data which can be used to design or to prove future missions that are going to be launched into the space, or for other type of applications like specific mapping. Another way to do that is to board the satellite into a radar. Therefore, we enter into the case of ground-based SAR systems. Okay, here you have the system we developed in the past. We have developing these systems. Okay, this initial system was able to work at X-band with polarimetry, with interferometry. Here you have one system of Italian colleagues, from Japanese colleagues. Which is the advantage of this system? Of course, this system cannot cover global. They can cover a very particular area, but with one particularity, is that the revisit time can be very short, and it can deploy continuously. For instance, in our system, or in the system we are developing now, we are able to take images every minute. Or these systems are very useful, okay, as early award systems. Okay, they can monitor an area, and maybe they can detect some difficult event, okay, that can be dangerous. For instance, the Italian systems, the system was used to monitor Mount Vesuvius in Italy, okay, the volcano. As I said before, one of the main characteristics of a SAR is frequency. We can have civilian systems working between 1 to 10 gigahertz, which is the frequency. The frequency basically determines how do we see targets, and particularly if we analyze forests, as the example shown here, because these images show the Amazonian forest, we determine penetration. Okay? Frequency, as we increase frequency, we increase wavelengths, so we see targets, we don't start to be invisible to some target, so we increase penetration. Okay? That's why, for instance, in the case of the X-band, basically all the forests look homogeneous because you don't penetrate the canopy. As we decrease the frequency, you increase the wavelength, you start to penetrate more. And this is what you see here, for instance, at L1. Okay, so you see a completely different scenario. These images are both the three images taken at the same time over the same forest. If you look at this detail here, this is a rain cell, okay, where the X-band is sensitive to the raindrops, so therefore we don't see we see nothing, and therefore if we increase frequency, if we decrease frequency, we increase wavelength, okay, we are less sensitive to the drops. The advantage is that this very old example shows how radar is almost insensitive to weather, and the main advantage is that it is not affected by the cloud cover, like the optical system. This is very important, for instance, in tropical regions where you have 70% cloud cover all the time. So on those cases, you cannot use optical images. Using radar images allow the penetration, so allow to create temporal periods. This is another example of Madrid, it's the capital of Spain in the south. So you see how these areas look like look like at these frequencies. You see some differences. This is another result. This is in the area of Santiago de Chile, the capital of Chile. So what you see is the different mountains surrounding the city. Okay, here you have a lake. So you can see especially how you look like, or how these images look like. And the main characteristic of these images is, as you see, mountains appear distorted. Okay, one of the consequences of geometry. Here you have another result. This is in the desert of Chuquicamata. Is the in the north of Chile. Is a copper mining. A hole made by humans. Is one inverse mountain. So this is a. The radar is flying from here to here. So you compress the sides looking at the radar, and you don't stretch the size of the mountain.
Sir, actually, I got confused between ascending path and descending path. Like, how can I distinguish my radar is ascending or descending looking at the image?
Looking at the image, you cannot. Purely looking at the image, if you know the area, the geometry of the area, the geology, you can identify that. But purely looking at the image, you cannot see ascending, descending. Okay, if you have two, you can, but a standalone, you cannot differentiate. Okay. By the image itself, sometimes in the metadata you have this information. Okay, so therefore you can derive. Okay, this is how the image looks like in Google Earth, and this is how it looks like in SAR. So you see the same effect of distortion. You see one side of the hole completely compressed because it faces the radar, and the other one is increased due to the fact that they are away from the radar. Also, if you look at this area here, this is the debris. Okay, look that the radar basically is flying in this direction. So basically what you see here is the shadow. Okay, because the radar is not able to see that due to the mountains. Other details, okay, this is from the US. This is at 35 gigahertz, so this is a super very high resolution. So you can see the cars, you can see the different areas, you can see the shadows of the tree, but this is not the optical shadow, this is the shadow at 35 gigahertz. Okay, and here you have some details. Here you have some an helicopter. So here you see the shadow of blades of the helicopter, so you can figure out the resolution you have. You have here a plane. You show the you can see the shadow of the wings.
Depend upon the wavelength also. Like if the wavelength change, shadow will also change, or anything to say. Like different frequency also will have the same shadow.
No, because the at P1 maybe the blades are transparent, because I'm not expert on aeronautics, okay, but sometimes the blades are made on plastic. So at 35 gigahertz, and also the blades are not super big, okay. So at P1 is about 3 meter wavelength, so you don't really see the area. So the rule of thumb, more or less, is that with a given wavelength, you see all objects that are more or less of dimensions larger than λ/2. So if we are talking about 3 meters, so you start to see objects above 1.5, more or less. And this is a more or less, okay?
Because of the antenna size, because you mentioned azimuth resolution is depending on VA.
Yeah.
Like that reduces.
Because there are other parameters that take place. Okay, the quality of the image depends on the dimension of the antenna, the SNR. So therefore, you need large antennas. So at the end, it's a kind of compromise. Because if you look at the equation, okay, make the antenna small. No, this doesn't work like that. Okay.
And how can you accomplish higher spatial resolution at 35 gigahertz?
Because you are at this frequency. I mean, also because at higher frequencies, legally, you can put more bandwidth. Yeah, this basically you can put more bandwidth. The quality factor. Okay, we have a detail. We can go also to other type of application. We can make a global coverage. Here I show the South American continent, or imaged by SAR images from ALOS too. In this case, what you can see is the Amazonian forest, the Amazonian river, the Argentinian Pampa, the Andes. You can see all the details. So you can go from very high resolution to super large. Nowadays, you have even application of global coverage. And this is the advantage of SAR systems operating on board satellites. Okay? Okay, so we have our instrument. Okay, we have our system that is capable of providing high resolution wide focus. Let's put it like that. So, what is polarimetry? How do we use polarimetry in the frame of radars? Okay, so the most important advantage of SAR systems is the fact that we can take multidimensional data. Okay, maybe you know we can obtain interferometry, differential interferometry, and so on. So in this particular case, we are going to explain a particular type of diversity, which is polarimetric diversity. So in this case, we won't have image, but we will have a collection. In some cases, 3, in some cases 4. Okay? For instance, in monostatic systems, we will have 3. In biostatic systems, like the Future Harmony is a system, and later on have some information about that. You will have 4 images. H different from H. So this is what most of the people think. Okay, I have diversity, I have 3 images. So my information is basically in the fact that I have more channels of information. But the advantage of SAR and the advantage of multidimensional system is not only the fact that we can have multiple images, but that we can have the correlation between images, how both images are correlated. And indeed, this correlation, which is complex because the images are complex, and particularly the phase of this correlation is the most important radar observable. In the case of interferometry, this phase contains the topographic information. So in the case of polarimetry, this phase contains the geometry of the target and also some information about the electric constant of the target, so therefore it is sensitive to content. Okay? So remember, when we are doing with polarimetry and in general with multidimensional SAR, we not only have a collection of images, but we have also these parameters, the correlation between the images. Okay? Later on, we will go to details on that. Okay, so we have the system, we have polarimetry. The question is, what is polarimetry? Okay, this is the fundamental question. And what we can do with it. And now is when it comes the hardcore mathematics. It's not very, you will see a lot of equations, but you will see, I will try to explain it very simple. Okay, so basically, when we deal with electromagnetic fields, okay, our background are the Maxwell equations. Okay, the Maxwell equations basically govern the generation, the propagation, and also the interaction of electromagnetic waves. Okay, so therefore, what we need to do is to solve these 4 equations. The solution is an electromagnetic field. Okay, which I indicating here, the electric field. So at the end, what we transmit and what we receive in a radar is an echo. But this echo is nothing more than an electromagnet. Okay? So this is an electromagnetic field. The most important thing is that it is a vector. The electromagnetic field is a vector, is not a scalar quantity, is a vector. And the second ingredient of this solution is that this vector varies in space and time. Okay, so an echo of a radar is nothing more than an electromagnetic field with a space and time variation. Okay, keep this in mind. The idea, before we go into the next slide, is that this vector cannot vary in space and time independently. Okay, variation in space and time is coupled, and this coupling is governed by the Maxwell equations. Okay, so therefore, this is a simplified version of a field. Okay, we are using electromagnetic fields. That means that we don't have a field component on the propagation. Okay, so if we propagate in the z direction, of course, the component we will have is only on x and y. So therefore, if you look at this plot here, my field are the red arrows, and as you see, is describing an helix. Okay, so the component in x is given in blue here, is this cosine, and the variation in y is given in green. So therefore, I can decompose each vector in these two dimensions.
I would visualize this polarization effect, both horizontal and vertical, but I used to simulate things like the wave moving in a water, whose amplitude is with time.
No. You cannot use that example. No, you cannot use that example because in water is a longitudinal wave. This is an electromagnetic wave, and totally different.
So how do you imagine like the wave? Because I think the
like a vector describing an helix in space, like this. Is a rotating vector. Is going like this. It's an helix. It's an helix. Later on, you will see the clearly. Okay, what I mean by polarization. Okay, so we have this vector. Okay, if we now pay attention to the shape described by the tip of the vector. Imagine that I make a cut in one position, and I start to the positions of the tip of that vector in this particular space through time. What I can see is that the tip of the vector describes an ellipse. Therefore, we call polarization to the shape, to this shape. This is the polarization ellipse. So as you see, polarization is nothing more than the vector nature of an electromagnetic field. When we refer which is the polarization wave, we refer to the vector nature of the wave. What is the point? The point is that this vector can describe any shape between a line and a circle. So you have infinite ways from going to a line, passing through an ellipse, going to a circle. Okay, so therefore, this is the shape. Okay, and the shape has different parameters. Okay, we have the amplitude, how big is this L? Okay, the absolute phase, which is alpha in here, is for T0, which is the phase of the field. We have the orientation angle. Okay, the orientation angle is how rotating, and also we have the ellipticity, how close, how far this ellipse is from a line of.
This is at the time instant.
No, in here we have removed the time. You will see later on. Okay. Here, when analyzing electromagnetic fields, we normally remove the time because we think that the don't change the frequency information. So we keep out the temporal information. You will see later on because I will try to simplify, okay? But as a first order approximation, this shape does not depend on time. So therefore, in order to describe the polarization of the wave, we need to describe an ellipse. Okay, it's very simple. Also, we have another parameter, which is the sign of the ellipticity. So the sign of the ellipticity in this particular case defines how we describe an ellipse on a side left or right-hand handed. Okay, because the ellipse can rotate like this or can rotate like that. Okay, so this is another parameter. So combining all the parameters, what we can have? We can have linear polarization. So here I showed 3 examples. On the top is horizontal. The field only varies on the horizontal dimension. Vertical. The field only varies in the vertical dimension. Linear or arbitrary linear polarization. The field only varies in a plane. So this plane can be rotated. Okay? So it can go from horizontal to completely vertical. Okay? So this is the linear polarization. And most of the SAR systems work into this linear polarization basis. And later on, you will understand why. First of all, because technically it's very simple. We can have the okay, we can have circular polarization. So therefore, we have 2 cases, left circular and right circular. And the sense is defined in the direction of propagation. You use the rule of the okay? So therefore, or the right hand rule. Okay? You define that, define what does it mean horizontal, what does it mean vertical. Left circular, right. And between the two, we have elliptical polarization. So we can have describe it in one sense or in the other. So therefore, you have infinite possible polarization states. So when we transmit a wave, an electromagnetic wave, an echo with a given polarization. Can be linear. GPS, for instance, use circular polarization to avoid the Faraday rotation effects. TV, geostationary TV, they also use circular to avoid the Faraday rotation effects. Weather radar, as far as you know, they use also circular to be sensitive to the shape of the drops. So you will polarization can be used to extract physical information. Okay, so how do we describe this polarization? As I have shown, we can first of all describe an ellipse, but there are many other ways to describe the polarization. So basically, the polarization ellipse at the end can be described only using 2 independent parameters. Okay? But a complete mathematical description needs 4 independent parameters. So therefore, in order to describe this polarization, in the literature, there are different ways to describe it. We will go to the Jones vector, to the one covariance matrix, to the Stokes vector, and we don't explain the polarimetric. But these are different ways to explain the same thing. Is the polarization of the. Okay, if we go to the Jones vector, basically the Jones vector is the minimum expression of the electromagnetic, of the polarization. So basically, this is the original, okay, expression. So what we can do is we can remove the temporal information. We also remove the propagation information. So therefore, the minimum expression we have is the Jones vector. So as you see, basically it contains the amplitude and the phase of each of the vectors. Of course, we have removed the time and the propagation information. So therefore, as we have removed the propagation information, we cannot define the sense of rotation, because we need the sense of propagation to define the direction of propagation to define the sense of rotation. Okay, there are different ways to define that. Some of the Some of the ideas, for instance, as defined by Lüneburg, was a German scientist. He tried to add a sign to the Jones vector defining the, so minus plus defines one sign or the other. So you can solve that problem. Okay, so as you can see, polarization is nothing more than a vector. Okay, it's complex vector, it's a spinor if you want. Okay, so each component is complex, has an amplitude, has a phase. What is the advantage of that? If we take one field, okay, we can decompose this electromagnetic field, this Jones vector, in this way. So basically, as the Jones vector is describing the polarity, there is a way to connect Jones vector with the ellipse parameter. The way to do that is to introduce this kind of expressions. Okay? Sorry?
What is the delta X and delta Y?
Delta is the phase of each of the components. Is the phase, the absolute phase of each field, okay? Okay, and this is one of the most important things. If you have to keep one idea today, and only one, is this one here. Basically, as it is a vector, we can decompose this vector in an orthogonal basis. Complex, eh? The only issue here is that this is complex. So therefore, we can decompose any field into a orthogonal basis. So as we are doing a vector, we are doing algebra. It's classical algebra. So the way the mathematics or the mathematical field to analyze polarization is algebra. So this has very important consequences. So therefore, as you can see, I can define, okay, any given or any field, okay, decompose as given of this transformation of the vector given in one of the components. So basically what we are doing here is transforming linear horizontal polarization in any polarization through this transformation. And the transformation is controlled by the alpha, the tau, and the variable, which is the polarization. Okay? So therefore, we can transform a linear polarization into a field of any polarization state. And this transformation is given by this rotation matrix. So therefore, if we have algebra and we have fields, we can start to play with the algebraic concepts. We can have the norm of a vector. We can define the scalar product, okay, with some particularity. Scalar vectors in or the scalar product is only possible on vector direction. So if we have vectors and we have a scalar product, we can define orthogonality. Okay, so if we define orthogonality, given one vector, I can define it one polarization, I can define the orthogonal polarization. Okay, so for instance, here I give one polarization defined by phi and tau. The orthogonal polarization is given by these parameters. Okay. So the idea is that if we have one polarization, I can define the orthogonal. So if we have linear, you can see that the horizontal and the vertical polarization states are orthogonal. If we go to rotated linear, P over 4, 3 times P over 4, both are orthogonal. If we go to circular polarization, right hand and left hand circular polarization are orthogonal. So we are playing with vectors and we And we have defined an orthogonal basis. The advantage of having an orthogonal basis is when we can define any vector, any polarization state in a given polarization basis, composing on the components of the. Okay, so the advantage is the following. I have my field, okay, and as we have seen, I can rotate, I can transform one polarization in the other. Okay, so I can make one, I can transform this linear polarization basis into a different polarization basis through this rotation matrix. I can do it on a second basis. If I combine both, what I can see is the most important property of polarization. Is that given one electromagnetic, given one in one polarization basis, I can transform it to any other polarization. And this transformation is deterministic. So what does it mean? This is what we call polarization synthesis. If I measure in a given polarization basis, I can transform it to any other polarization basis. And this is why radar systems work at a linear polarization basis. Because if I measure at this polarization basis, I don't need a second system measuring on a circular polarization basis. I just transform offline. Okay, so therefore, we only need to measure in a orthogonal polarization basis. Okay? This is polarization. Another descriptor is the wave covariance matrix. So in this particular case, it's a second order descriptor, which is basically given in here. It's a matrix. I multiply the components. The advantage is that as it is a matrix, I can also decompose this matrix. And this matrix decomposition or the 2x2 matrices can be decomposed on the very nice Pauli set of matrices. So if you make these decompositions, at the end, the components of the decomposition of this matrix on the Pauli basis are the so-called Stokes parameters. It's a different way to describe the polarization. Okay, so it's G0, G1, G2, and G3. Of course, I can relate everything. Remember that everything describes the same, the polarization of the ellipse. So I can establish the relation between all of them.
Okay, so what is the significance of like changing the basis from linear to right circular, side circular to 45 or something like that? Because I can imagine only like the linear one, but what advantages we have?
Because measuring in a single polarization basis, I can explore all the space of polarizations. So for instance, I can find the polarization state that maximize the received power. You can start to explore this polarization space offline. For instance, PolInSAR tries to maximize the quality of the phase. So the advantage is that I can explore the polarization space. It's an infinite space I can explore. So therefore, if I explore the space given a loss function, I can optimize one thing. For instance, received power. Okay? So therefore, here just to show you that Jones vector is related with the Stokes vector, also with the Jones parameter, also with the polarization lattice parameter. So everything is related. So in the same way I define it orthogonality with the Jones vector, I can define orthogonality with the Stokes vector. Very simple. Okay? What is the problem? Okay, the problem is that we need to distinguish one of the things. Remember that when I defined the SAR, okay, I defined the resolution cell by so if within that resolution cell I have only one target, every time I measure this target or similar targets, I obtain the same response. So therefore, the polarization backscattered by that target is deterministic. So therefore, the polarization is always the same. So in that case, okay, we say that completely polarized wave. The polarization doesn't change in space or time. Nevertheless, when we hit natural targets, the natural targets change. You have a forest, all the pixels are forests, but they are different forests. The problem in there is that as this forest changes from pixel to pixel, the leaves change, the polarization changes. But the change of polarization is random. So we need new ways to deal with a random polarization. In this case, we are facing partially polarized waves. The problem is that when describing partially polarized wave, we cannot use the previous descriptors. Why? Because if we have a random quantity and we take the expectation, we end up that the mean value of the fields is 0. So they are not useful. So we need to go to second order descriptors. So one of the second order descriptors that is useful for that is the stock vectors of the wave covariance matrix. Because if you make the expectation of the elements, these expectations are no longer 0. Because the expectation of EXX or Y is the power on each of the two components, and the diagonal term, okay, is the correlation between the two fields. So in this particular case, when I'm using distributed targets, distributed polarization, okay, partially polarized wave at the end, these elements are not 0. And this also translates the stock vectors. Okay? That's why when dealing with natural targets, we cannot describe the wave of the wave at the end, the polarization of the wave, with a given deterministic element. Okay? Okay. Here we have described the polarization of a wave. What happens with a target? The idea is that I send an electromagnetic field with a given polarization. The target changes the polarization. The echo has a change in the polarization. So I need to figure out some properties of the target according to the change on the polarization. That's the idea behind wave polarimetry. The classical example is this, okay? It may seem complex, but it's very simple. So look, I have my incident wave, okay, which is divided in two polarization states. It's in a basis. So if this incident wave hits, in this particular case, the interface between two media with different refractive index, what do we have? One of the waves will go on the second medium and another wave will go away. Okay? And if you see, okay, in this particular example, because it's very simple, flat interface, okay, you see that the fields have also a polarization. Okay? So how the change in polarization is considering here is the Fresnel coefficients, which basically depends on the relation of the refractive indices and the incidence sum. Okay? So therefore, okay, if I have my incident field and I have my scattered field, imagine that I have a transmitter here and a receiver in here. Okay, so I have this polarization, I have this polarization of the scattered field. I can relate both, okay, through this matrix. And what does it contain? Does it contain this matrix? The Fresnel coefficients. And the Fresnel coefficients depend on the refractive index of the medium and the incidence angle. So therefore, this element contains properties of the target. The $1 million question: how the hell I extract information from here? Huh? That's where the fun starts. Okay. This is in this very particular example. Okay. In reality, we have not a flat surface. We have something more complex. So what we have is the scattering matrix. Okay? And a polarimetric system, what it measures is this matrix in here. Okay? We have the incident field, we have the scattered field, both are related with this scattering matrix. The scattering matrix is determined by the target. So therefore, I want to infer some properties of the target from the shape of this matrix. Of course, this matrix depends on the target itself, on the shape, on the material, on the content. This is the information I want to extract. But also depends on the frequency, as we did before, depends on the geometry of the measure, the incidence angle, also depends on the coordinate system to measure the electromagnetic wave. Okay, and the most important thing is that all the elements of this matrix must be measured at the same time. Okay? Because if the target is changing in time and we measure these elements at different times, we are measuring. So you have to measure all of them at the same time. So here you have some examples. Here you have one sphere, the dihedral corner reflector, dihedral corner reflector, short cylinder, left-hand helix, right-hand helix. Okay, all of them, assuming that is a point. I have only one target observed by the SAR system. So you make the equations, you can see that the sphere has this matrix. Okay, the dihedral corner reflector has this matrix, and the tetrahedral has this matrix. So as you can see from the shape of this matrix, I can identify my target. Here you have some helices, left, right, the short cylinder. For instance, in the case of the sphere and the case of the trihedral corner reflector, both have the same matrix. Okay, so therefore these two cannot be. Okay, only with some prior knowledge. But the advantage is that as I have more measures by the system, I have a better characterization of the target. How do I describe these targets? Of course, the scattering matrix, okay? Before, but sorry. So here you have the scattering matrix. So if I remove the absolute phase, because it's something which is standard, I end up with 7 different independent parameters. The amplitude of the channels plus the 7 phase difference. So therefore, automatically, I have 7 parameters to characterize a target. So therefore, I characterize the target better. In a case of monostatic system, which is basically the transmitter and the receiver are on the same position, okay, in this particular case, SHB is equal to SBH, so I have 5 independent parameters to characterize. So of course, biostatic systems offer more parameters for a better characterization of the targets. You have 7 in front of 5. What other types of parameters we can define? And this is one of the most important breakthroughs in the case of polarimetry. Somehow is to transform this matrix into a vector. This may seem very naive, but it will give a lot of advantages on the exploration of the information. So if I can arrange this vector as a matrix, this matrix as a vector, sorry, okay, I can have this decomposition in the case of the lexicographic scattering vector, okay, so therefore I end up with a simple concatenation of all the elements of the matrix. Of course, as the elements are the same, the number of independent parameters is the same, 7. In the case of the monostatic, I have 5. Okay. There is a second basis, the Pauli basis, where I decompose these two by two matrix, the S matrix, in the same Pauli matrix I used before. So in this particular case, I have some combination of these parameters, HS plus BB, HS minus BB, HS 2 times VH, etc. But as it is a combination, the number of independent parameters is the same. Okay? What is the advantage of these parameters? As we know, these parameters, the combination gives more clues about the physical information. In the monostatic case, of course, we have 5 independent parameters. Which is the physical information context? If we go to HBB, whenever this term is big, we can assure that we are in front of surface scattering. Whenever HS minus BB is large, we are facing double bounce scattering. Okay? And whenever HB is large, we are in front of volume scattering. So therefore, what is the message of this slide? Polarimetry gives information about the geometric properties of. We can differentiate the geometry. Here is the same image as I showed before, one in Madrid. What happens if now I color code each one of these channels? So basically, polarimetry gives color to the image. And remember this is only partial polarimetric information because this combination does not contain the correlation between the images. Okay? But still, it gives very useful information. So remember, HS plus BB is important on surfaces. So therefore, whenever I have blue, it's surface scattering. So this is what I identify here. Whenever HB is large, it's volume scattering. Where do I have volume scattering in this image? On this river, where you have agricultural fields, and on these mountains, where you have. And finally, when do you have HS plus BB? On double bounce. Here, you have a red line. So basically, what you have here is the double bounce of a power line. I mean, the reflection of a metallic component is very high, so therefore is what we see the power line in there. Okay, because we see the reflection between the ground and the power line. Okay? It's a large type. Here is the image of Santiago de Chile, as I presented before. If we color code the image, given the polarimetric information, we can identify the lake, which is a surface. We can identify the top of the mountains, because as the mountains are so high, there is no vegetation, it's bare surfaces, so therefore you have surface, and below that threshold or that point, you have volume scattering due to the forest. If you go to the city, okay, you see some areas in pink and red, so it's a proper double bounce. And this is due because the streets are well aligned with the radar. Whenever you don't have this alignment of the street with the radar, you don't have a proper double bounce. You have multiple scattering. That's why you see some areas of the images in green, because it's multiple scattering. Okay, this is another result. Okay, this is in Oberpfaffenhofen, this is close to Munich. So airborne, that's why you have such a big resolution. Okay, so what do you have? Do you have green in these forested areas? Okay, you have red in these crops because this crop is due to plants which are super vertical, super well defined. So you have double bounce in there. And on the other area, for instance, here you have surfaces because they are blue. Okay? What is the advantage of this? I can make the transformation. As I said before, if I can transform the electromagnetic fields in any basis, I can do the same for the target. So therefore, what I can see with the polarization synthesis is what is called the consimilarity transformation. I can transform the S matrix to the S matrix measured in a different polarization.
So therefore,
I can start to explore how targets behave according to polarization. So therefore, I have even a better characterization of the target. So I can, with measuring in a single polarization basis, I can synthesize the answer or the response of the target at any polarization basis. So I have an even better characterization of the target. Okay?
so this is what
I have done here. I have transformed these targets into a second polarization basis, which is plus 45 minus 45.
So you see,
The colors change completely. The interpretation has to be according to the new basis. I can also transform to the circular basis. This is the image taken by the real system, the system measuring an horizontal vertical. This is the synthesized image of a system measuring in circular and circular left, circular right polarization basis. So I don't have really this system. I have synthesized that.
on the other side,
If I would be that system,
it will measure that.
therefore I can explore this synthetically at home. That is the advantage.
And I
And not only calculate this answer or this response at a given polarization, but at any polarization. Okay?
Fully describes that, or there is some limitation. Is that fully described that?
It's fully described. With fully polarimetric data, if you measure the complete scattering matrix, is fully characterized.
It is as if that circular polarization.
Mhm. Mhm.
Of that batch. When you are transforming the polarization basis, why it is changing the inherent nature of the target, like that the color thing given the poly basis, the odd static, it is getting converted volumetric scattering.
No, of course it's volumetric scattering, but the type of answer here, okay, is referred to the power in this polarization basis. So it's the analysis of the volume scattering at a different polarization basis. But of course, one thing is how I measure the target, and another different thing is the target itself. I don't change the target. I change how I measure the target, which is different. So another problem. The idea is how to interpret this. Yeah. At the moment, we have to be honest. We have only analyzed mainly into this basis. Okay, we are not really analyzing on this basis. Or as we don't measure in as we have the capability to explore all the space, I didn't explain it here. We have we can define the description, we can define a polarization system to look at. We can analyze not the target at one given polarization, but at all polarizations. So you analyze the whole set, not just one particular or the other.
Like that, whenever lights are, so the difference will be changed, like volume, surface, and the double bounce.
Yeah.
That will be changed, like that will not be the same when it was the linear polarization.
They appear different in another polarization. Of course, I mean, volume is in linear or circular or in elliptical. They will appear different. But at the end, I'm not particularly interested in given polarization. At the end, as I can explore all of them, I'm interested in the complete polarization signature. Is how the target behaves at any polarization. I mean, that's the advantage. I can explore all of these. So why restrict myself to one of them, or two, or three? Okay, I explore all of them.
You are saying that the right side image, that colors can have different meaning than the left.
Yeah, because the colors refer here to the combination which in one circular polarization I receive in the other. So the physical interpretation is a bit different.
So they will represent the same physical.
It represent the physical. So therefore, as I represent the same physical mechanism in two different ways, I have a better characterization. That's the idea. But I don't have only two, I have infinite. So therefore, I can have a very accurate differentiation of the geometry of the target.
How close when you are measuring in some polarization and then you are.
Repeat again, sorry.
Yeah, what I'm trying to is you are measured in some four different polarizations, and then now they are trying to explore a character the target in left hand circular, right hand circular, or that. Then when you actually measure that with a system available right now, is only decomposed and then transformed. Actually, if you measure, then how close this transformation would be with respect to the actually measure, whether they tally?
It will be the same. I mean, if you have because at the end, the transformation is purely mathematical.
As it is mathematical.
Yeah.
I'm saying when you really put a sensor and then look at that particular wavelength or
If
you were able to succeed in that measure, but still you have to meaning
the response will be exactly the same. I mean, without entering to the technical differences, just ideal system. Okay. Okay. So, what is the advantage of this description? Is that I can define this outer product. So I define this T matrix. Despite the large number of elements, it comes from this. Okay, so still the number of independent parameters is 7. In the case of a biased monostatic case, it's 5. Okay, what is the advantage? With this new T matrix, I can also apply the rotation. So I can generate the T matrix for a different polarization basis. Also the same for the bias, for the coherency matrix. Okay, 7 independent parameters in the biostatic case, 5 in the monostatic case. You have all the mathematics. Okay, and I can transform. So this is the most important advantage. You have to remember that polarimetry allows to synthesize. So what polarimetry gives me is an infinite space where I can explore synthetically the target. So I can find the some possible ways how to explore the polarization space. I can maximize the received power. I can maximize the received power while minimizing the noise, super the clutter. I mean, all these kind of things. Okay. In the case, if someone you have worked with polarimetric SAR interferometry, what polarimetry allows is to give me the phase with the less speckle effect. Okay, to optimize the quality of the phase, for instance. Okay, so this is where we are. We have the S matrix, we have the KL vector in the Pauli matrix. In the biostatic case, we have 7 different parameters. We have 5 different parameters. From these vectors, we can define the C matrix, the T matrix, and in the case of the S elements, we can define the inner matrix. This is a map, or think as this figure as a map. I wanted to look at it as a map. All of them are equivalent.
I have a diameter reflector, corner reflector.
Yeah.
Placed with the linear basis. I measure it with the S matrix and the T matrix. Then I have I place the same matrix in the LL and the RR.
Well, you will obtain a different matrix, of course.
Yeah, the matrix. I mean, the same reflector is placed.
Yeah, but the
signature would be,
the signature will be different.
so the double bounce become a volume scatter.
No, it will be a double bounce, but represented in a different basis. The numbers will be different, but they will represent the same nature. That's, you have to keep that. I changed how I measure the.
What are the two independent parameters that are different from biostatic?
In the monostatic case, when you have the transmitter and the receiver, the HV and the BH channel are the same. That's why you reduce two, one amplitude and one phase. Okay, targets equal to BH. Okay,
It would be different in bispecific.
I think they are different. Okay, after all, I will present the admonition. Okay, with some system. Okay, so this is a map. Okay. From here, I can obtain the stock vectors, K matrix, C, T, KP, KL, S. So the question is why I make my life difficult with so many things. Okay, that's the question. Why I don't stay here and make my life very difficult? 2 minutes, I will stop. Okay? Remember, before I presented deterministic totally polarized wave, partial polarized waves. One deterministic, the other random. So therefore, how this translates to if I go from monostat with deterministic target to distributed target, and I have to assure you, most of the targets are this type, okay? What happens? The polarization is random. So I cannot use single or first moment order descriptors. What happens? The expectation of the S, KL, and KP are 0. So therefore, these are 0, sorry, and the expectation of the C, of the T, and K are not 0. Second order descriptors. Okay, this is what I try to write here. Okay. And the most important thing is that I lose my connection with this. So the idea is that at the end, on natural target, I can only explore the C matrix or the T matrix or the K matrix because these guys here are unequal to 0. But from a physical point of view, I know how to interpret these guys here. So polarimetry at the end, and what it will follow is how I restore this connection. How I interpret physically these second order elements. Okay? The idea is the same. The advantage is when I go to the second order descriptor, I even increase my number of parameters. Okay? So what we are going to see now is the explanation of this, why I lose this connection, and how I restore. Okay? Just for you, all these theoretical aspects are considered in this book. Okay? I recommend you go because the book is open access. Okay? You can, chapter 1 contains all this. The book is free to download. Okay? It was this was a project funded by European Space Center. Okay, so there is the important part of the book is not the theory, but all the subsequent chapters deal with all the applications nowadays that polarimetry data. I recommend it to you because this work was a collective effort of people. Okay, contribute to different applications. Okay. So let's go to the next part. Let me see if it works. Okay. Yeah, but so let's go to the next part. Okay. Remember polarimetry. Our problem is that in natural target, our polarization is random. Why is random? That's the question I want to answer with this second presentation. Okay, why we need all this complexity? Okay, so here you have again contact information if you want to put me questions. The answer, okay, And what we are going to do here is to introduce the concept of spectrum. Okay? The spectrum is the kind of bad guy into this guy. Okay? Is the guy making my life easy. So, first of all, let's go into explain what is spectrum noise. Okay? So, here you have an area of Oberpfaffenhofen as taken in the SAR polarimetric sensor, how it looks like through an optical. Okay, thank you very much.